Good morning, Professor Yao. It is our pleasure to introduce our final project to you here. My name is Liu Minghao and my partner is Mi Jianle. So without further ado, let's get started. These are our contents and I would like to introduce the first two parts and my partner will continue the remaining parts. Now let's come to the first part, introduction. The prediction of short-term returns in cryptocurrency markets is a passion issue for traders and investors. Therefore, we utilize several machine learning methods and models such as RNN, light GBM, linear regression, KNN decision tree, SVM, random forest, and elastic net to forecast the short-term returns of 14 well-known cryptocurrencies. After applying different models, we conclude that light GBM is the best performing model for predicting 15-minute visualized returns in cryptocurrencies among the approaches that we have used. Now here comes to the next part, data pre-processing and feature engineering. As for data pre-processing, we notice missing values in the VWAP and target columns during data pre-processing. A sequential feeding strategy is used to populate the missing values of these two columns one by one with the previous non-missing values in each asset ID group. We select the data after 2020 as the training data due to computer memory limitations. In terms of data analysis, we examine the correlation among various cryptocurrencies in the training dataset. After examining the correlation among different cryptocurrencies, we discovered robust correlations between certain cryptocurrencies. We have provided the correlation plots to demonstrate our results. Besides, we have also provided the dynamic correlation plots within some of pairs mentioned above. This correlation analysis offers a foundation for selecting the appropriate model for prediction. These are dynamic correlation plots. We take the first plot as example. We would observe that the dynamic correlation between Binance Coin and Ethereum keeps an extremely high positive level within nearly the whole time interval. As for feature engineering, we have generated some new features from the original dataset. These features are listed below. Inside each feature, we have defined some functions to achieve our goals. These additional features can enhance the model's capability to comprehend and anticipate short-term returns. Now my partner will continue the remaining parts.
So I will talk about the model training part. So we train and evaluate the training data by using various machine learning models. First, define a CV result function that uses the time series split to split data into training and testing data. And after that, we calculate the correlation coefficient between the predicted value and the testing value in each fold. We use the fivefold cross-validation, so the function returns the average of the correlation coefficient across the five folds. We first use all training data regardless of the specific asset ID for the training. And then we train the LGBM regression model and turn the parameter. The function train LGBM function is to train and optimize an LGBM regression model through the grid search and return the best model found. In the function, we define a parameter grid with three parameters: an estimator, subsample, and learning rate. So after adjusting the parameters, we found that the optimum parameters for learning rate equal 0.1, an estimator equal 100, and subsample equal 0.6. We also trained other models such as linear regression, KNN, decision tree, ElasticNet, support vector machine, and RNN. So for the RNN, the model is trained by using the add-on optimizer with the learning rate set to 0.0002. The loss function is mean squared error. Since training RNN takes a lot of time, we did not perform the five-fold validation on it. We only selected the first 75% of the data in the DF train as the training data and the last 25% as the testing data. So for the model evaluation, as it can be shown in this graph, the correlation coefficient between the predictive value of the large GBM model and y-test is the highest, while the correlation coefficient between the predictive value of the decision tree and y-test is the second highest, while the remaining models perform worse than the LGBM and the decision tree. We also analyzed the reason behind this different performance. So the lower accuracy of the linear regression may be due to the overfitting, sensibility of linear regression to outliers, and multicollinearity. The high-dimensional data make linear regression more sensible to the overfitting since the model is more likely to learn from the noise and ignore the general pattern. In the presence of the highly correlated features, linear regression may suffer from multicollinearity issues, leading to the model instability or overfitting. While on the other hand, the light GBM is an efficient, scalable, flexible, and gradient boosting model suitable for the high-dimensional data. It is especially suitable for processing large-scale data and high-dimensional features. Therefore, large GBM performs best in these models. So we also calculate the weighted correlation across all assets for linear regression and random forest. So first, we let the weight of the weight column in the DF asset details, and the result is stored in a list. And then we use the group by function to group the DF train data according to the asset ID column and store the data frame of each group in a dictionary assetdict. Then we call the function weighted correlation to calculate the weighted correlation of each function. The results show that using linear regression, the weighted correlation of the 14 assets is around 0.01, and the weighted correlation of the random forest is around 0.04. So next, I will talk about the conclusion and future work. In this project, we use various machine learning models to do the short-term return prediction, and we conclude that the large GBM model could predict most precisely among all the models we selected. We also had some limitation in our research. First, the selection of the assets feature is limited. And second, we also need to conduct more in-depth research to analyze the reasons behind the differences in the performance of these models. So that is the end of our presentation, and thanks for listening.